Welcome back, everybody, to the first session of the afternoon talks. Our first speaker will be Tom Wong from Creighton University. He's going to be talking about Lackadaisical quantum walks with symmetry breaking.
Thank you for the introduction, and thank you to the organizers for having me. It's a pleasure to be able to join this meeting virtually. So I'll be talking about some work that I did with Jacob Raposa, who was one of my students at Creighton. So Jacob is actually in our 3-2 program, which means that Creighton doesn't have an engineering school. So we partner with Washington University in St. Louis that does have an amazing engineering school. So they do 3 years at Creighton and then 2 years at Washington University. And then when they graduate, they get a BA from Creighton and a BS from Washington University. So that allows them to do all the engineering prerequisites with us and then study engineering there. So Jacob started doing this research with me the summer before his freshman year. He finished it by the end of his sophomore year. And then he just finished his junior year at Creighton, and then now he's going to be starting at Washington University in the fall. And so this is published in Physical Review A. There's on the screen, you can see there's the journal article, and it's also on the archive, so you can find it there as well. All right, so many of you have heard me talk several times about Lackadaisical quantum walks, and so we're going to start with just a quick refresh of that. So let's look at search on the complete graph, which is an auto-on network, say of n vertices. So in my drawing, I picked 6 vertices. And the idea is that we're trying to find a particular marked vertex. And we do that by querying an oracle. And so what we do for a quantum walk is we start in a uniform state over all the vertices. So in the drawing there, there's 6 vertices. So we start off by guessing each vertex with probability 1/6. Because when you start off, any vertex is equally likely to be the marked one. In my drawing, I made it the first one with that, indicating it with a double circle. But the idea is that we don't know that in advance. So we start with a uniform state or uniform guess, and then we do a series of steps where we query an oracle. We apply what's called the Grover coin. So this is a coin quantum walk. So we apply the Grover coin, which basically shuffles the different directions that the walker can point. And then we do a flip-flop shift, which causes the walker to jump and then turn around. So I'm not going to get into the definitions of these things because a lot of people already know them. But basically, we're searching using this type of quantum walk. To make this a lackadaisical quantum walk, all we do is we add self-loops of weight L to all of the vertices. So now there's some probability of staying put. So that's where the lackadaisical or the lazy part comes in, that you're not always going to jump away. You might just stay where you were. And L can be, any non-negative real number here. And one of the things I want to point out that's relevant to this new work is that if you add these self-loops of weight L to every vertex, you preserve the symmetry of the graph. And what I mean by symmetry as a physicist, very imprecisely, what I mean is the graph before was vertex-transitive. If you add these self-loops of equal weight to all the vertices, the graph is still vertex-transitive. So you're preserving that symmetry. So let's see what happens with this walk. So let's look numerically at search on the complete graph with 1,024 vertices, starting with no self-loops, or if all the self-loops have weight 0. And what happens is the success probability starts off at 1/1024, which is very small, or near 0. And then as you repeat each step where you query the oracle, apply the Grover coin, and then do the flip-flop shift, with each one of those combined steps, your success probability ends up growing until it reaches about 1/2 after about 20 steps of the quantum walk. And then it goes back down and it's quasi-periodic. And so the idea is at this point, this is when you want to measure the position of the walker. And with probability 1/2, it is at the marked vertex that you're trying to find. Let's see what happens if we make this a little bit lazy by making the self-loops have a non-zero weight. So let's say it has a weight of 0.3. So what happens now is that the success probability, again, it starts at 1/1024 because that's how many vertices there are. And now when it grows, as we keep taking steps of the quantum walk, we see it reaches a higher value. So instead of peaking out at about 1/2, it peaks out at about 0.7. So this is better. So now if we measure the position of the walker after about 30 steps, then with probability 0.7, we'll find that the walker is at the marked vertex that we were trying to find. If we make it lazier still, say L equals 1, we get this. So now the success probability actually reaches 1, which is great. So after about 25 steps, if we were to measure the position of the walker, we would find that it's at the marked vertex with probability 1. And if we make it lazier still, say L is 2, it actually gets worse. So the best value in this case for the complete graph is for L to equal 1. Okay, so this is an old result that is actually proven as well in some old works that I did. So just to tell you the result, for large N, you can show that the success probability, so those wiggly curves from the previous slide, that curve follows this function. You don't need to remember this or anything, where alpha is this funny thing. You don't have to know this. The point is, like, we can analytically prove what happens on the previous slide for large N. And in particular, if you use these values, you can show that when L is equal to 1, you get a success probability of 1 at time pi over 2 times the square root of n. So this searches in square root of n time. So this is the quantum walk version of Grover's algorithm. So let's go to the newer material, which is, oops, I hit backwards. Okay, which is what happens if we allow the self loops to differ. So in our picture, now instead of all 6 self loops being the same value, they can all take different values. So this one could be 0.1, this one could be 0, this one could be 5, this could be 7.2. The idea is that they can all differ now. And what that does then is that it breaks the symmetry of the graph. So the graph is no longer going to be vertex-transitive, because if they have different weights, the vertices have a different structure to them. Until for my language, I'm thinking as a physicist, you can translate it into more precise math terms. And so this is what we mean by search with symmetry breaking. And so what we're going to do is we're going to repeat the previous simulations where we had those graphs. And what we're going to do is at the marked vertex, we're going to use the same values as before. We're going to let the weight of the self loop be 0, 0.3, 1, or 2. And then for all of the remaining vertices, we're going to let them take random values between 0 and 10. And let's see what happens. Let's see if by making all the other weights random, if we get a different evolution. So let's do that. So first of all, if the marked vertex has a weight of 0 and everything else has a weight between a random weight between 0 and 10, and it can be like fractions, like it can be like any real number, 0 and 10, or floating point number. I did this numerically. We get this curve here, which looks basically the same as what we had before. Right? After about 20 steps, you reach a success probability of a half. When we have a weight of 0.3 at the marked vertex and random between 0 and 10 everywhere else, we get basically the same thing as before. When L is 1, you again get the same thing as before, and when L is 2, you get the same thing as before. So let me actually put them side by side so you can see them. So this is what we had originally, where every self loop had the same weight. And then this is what I just showed you, where the weights of the self loops at the unmarked vertices are random between 0 and 10. And if you look at these two, they are very similar. To the eye, essentially identical. But if you look at the numbers, there are, of course, slight differences out to some number of decimal places. But basically, they're the same. Very similar. And so, it looks like we can break the symmetries of this graph, and it seems like nothing changes. The only thing that seems to matter is the weight at the marked vertex. So where we went from 0 to 0.3 to 1 to 2, that was the weight at the marked vertex. And the weights at the unmarked vertices, it seems like it doesn't matter. We can just pick them to be whatever random value, and it seems like the evolution is the same. So, interesting. Well, let's see if we can prove this. So for the general case, I'm actually not able to prove it. And so, what does a theoretical physicist do when faced with a situation like this? Well, there's two things. First thing is you prove a simpler case, a special case that you actually can, where you actually can do the math. And the other thing you do is you go to a conference and you talk to mathematicians and you hope that they can solve it. So this is another installment of Tom has an interesting observation and he needs help. So the special case that we were able to prove, excuse me, was where you only have two different weight self-loops. So let's say M of the vertices have self-loops of weight L. So let's look at our picture of the complete graph with 6 vertices again. Let's say 4 vertices have self-loops of weight L. And then the remaining 2 vertices have weights L prime. So the idea now is instead of having 6 different weight self-loops, we just have 2 different weights. And this, of course, makes the analysis much easier, reducing the number of variables you have. And we were able to prove that in this case, the only thing that matters is L, because you can see here that the marked vertex has weight L, as do these other 3 here. And basically L is the only weight that matters. L prime doesn't. So so I'll just give you a sketch of the proof. I'm not going to go into the details of it, but the idea is that this problem evolves in a fixed 9-dimensional subspace. So let me show you a picture here. So the marked vertex, I've colored A, and then all of these other vertices that also have weight L, all of these I've colored and labeled. I colored blue and I labeled B, because all of these are going to evolve identically to each other because of the symmetry of the initial state and the quantum walk that we use. And in these vertices that have weight L prime, these are going to evolve identically to each other. And so there's really only 9 different values to keep track of, if you will. So there's the A vertex. So imagine the walker is at A and it can point to itself, and it does that with some amplitude. You can have the walker at A pointing to the B vertices, and it's going to point to all the B vertices with the same amplitude. And you can be at A pointing to the C vertices, all with the same amplitude. And so that corresponds to these 3 states I'm calling here: A pointing to A pointing to B, and A pointing to C. If you're at a B vertex, you can point to A with some amplitude. That's A. You can be at B pointing to another B vertex, and those are going to be the same amplitude. That's B, B. And then you have B pointing to C, and finally you have C pointing to A, B, and C. So the idea here is that you can shrink things down to a much smaller subspace. Once you have that small subspace, you can express your search operator, where you have your oracle query, your Grover coin operator, and then your flip-flop shift. You can then write this as a 9x9 matrix in the subspace. And once you have your 9x9 matrix, you can find its eigenvalues and eigenvectors for large N using degenerate perturbation theory. So you have their eigenvectors, the psi1 through psi9, the eigenvalues. Because this is real and unitary, they're going to be in the form of some complex exponential. So once we have these eigenvectors, we can express the initial state as a superposition of those eigenvectors, or linear combination of those eigenvectors. And then if we evolve, we're just applying u t times. So each time we apply u to an eigenvector, we're going to pull out its eigenvalue. And so what we get is the same initial state, but with each of these eigenvectors multiplied by its eigenvalue t times. So this would be e to the I lambda 1. Oh, I guess I called it theta here. It should be theta 1 then, and theta 9. So the idea is you can do this math, and you can show then for large N that the success probability, so the wiggly curves that we're going up and down, that you get the exact same formulas as we did previously when all of the self loops had the same value. So that proves that they evolved the way for large N for that special case when there's only 2 different weights for the self loops. Are there any questions so far? I don't see anyone jumping to the mic, so I'll continue. So a reasonable question to ask is, well, this works for the complete graph. Does it work for other vertex-transitive graphs? And so we numerically explored a bunch of them. We looked at regular complete bipartite graphs, Johnson graphs, strongly irregular graphs, arbitrary dimensional periodic square lattices, so like square lattices, cubic lattices, 4D, 5D, so forth, and hypercubes. So let's look at some of the simulations to see if we can see any trends. So here we're looking at search on the regular complete bipartite graph with 256 vertices. So you have 128 vertices in each partite set. And since this is a bipartite graph, and sorry, since this is a complete bipartite graph, the degree of this is 128 because every vertex is adjacent to everything in the other set. Okay, so let's see what happens. So first of all, if all the self loops have weight 0, so basically if there's no self loops, this is what happens. So after about 18-ish steps, 18, 19 steps, you reach a success probability of a half. So again, after this many steps, if you measure the position of the walker, you find that it's at the marked vertex with probability a half. If we make all the self loops have weight 0.5, we see that the success probability reaches 1 now, which is great. And now what we're going to do is we're going to let the marked vertex still have a weight of 0.5 for its self loop, and then all the remaining 255 vertices will make their self loops random between 0 and 10, just like we did before for the complete graph. So if we do that, we get that dotted green curve, which you see lines up very well, not exactly, but very well with the dashed red curve from before. So again, we see that it seems like the weights at the unmarked vertices don't matter, because you can just make them all random if you want, and you basically get the same evolution. So, or another way to say that is that only the weight at the marked vertex matters. The weight at the unmarked vertices don't. So the regular complete bipartite graph, that's consistent with what we learned from the complete graph. Excuse me. Now let's look at the Johnson graph. This is a Johnson graph with 252 vertices and degree 25. So with no self loops, we get this curve, very similar from before. With all the self loops having weight, 0.099, we get a success probability of 1. And now if we make all the unmarked vertices have random weights between 0 and 10, we get this green curve, which again is pretty close to the red curve. Not exact, but pretty close. What we're seeing again is evidence that it seems like only the weight at the marked vertex matters. Let's look at a strongly regular graph. This is a Paley graph with 257 vertices and degree 128. So with no self loops, we get this very familiar curve. With all of the self loops having weight about 0.5, 0.498, we get a success probability of 1. And if we let all the unmarked vertices have random weight self loops between 0 and 10 as before, we get this dotted green curve. And again, we see some good agreement with the uniform case. So again, we see that only the weight at the marked vertex matters. The weight at the unmarked vertices don't seem to matter. So hopefully you're seeing a trend here. Now let's look at periodic square lattices. So this is a 2D lattice that's 16 by 16. So it has 256 vertices. And this has degree 4 because it's a square lattice, right? You have a neighbor above, below, left, and right of you. So with no self loops, we get this curve here. It doesn't reach a half for the 2D lattice. If we let all the self loops have weight 0.0156, we get a success probability that's close to 1, which is a great improvement. And now if we give all the unmarked vertices random weight self loops between 0 and 10, so the same thing we've been doing, we get this. That's not the same now. So what should we try? Maybe n is too small. So here n is 256. Why don't we try a bigger 2D square lattice? So let's go ahead and try one that's 32 by 32, which has 1,024 vertices. And of course, it still has degree 4, because it's still a 2D square lattice. So if we have no self loops, we get this. If all the self loops have this same value, it jumps up to 1. And if we give random weights to the unmarked vertices, again, it's basically just as bad as we had in the previous slide. So it seems like this is not an issue of n not being large enough, because we just made n bigger, right? We went from 256 to 1024, and the red and green curves line up just as poorly. And so we might ask, well, what else can we try? Well, instead of changing the n, what if we try smaller random weights? So instead of picking the random weights to be between 0 and 10, why don't we pick them to be between 0 and 1? Again, they're random numbers, right? So decimals between 0 and 1. So if we do that, we get this dot dash blue curve. And now we are seeing good agreement with the homogeneous case, with that red case, where they all have the same weight. So there's some observations we have from this data. Oh, and also let's go back to the smaller graph, the one where we had 16 by 16 or 256 vertices. So if we also make the random weight smaller here, between 0 and 1 instead of 0 to 10, this one's also improved. So it seems like for both of these 2D square lattices, if we just make the random weight smaller between 0 and 1 instead of between 0 and 10, that we're improving the agreement with the homogeneous case. So, okay, some observations. So it seems like the random self-loops have to be small relative to some quantity. And that quantity is not n, the number of vertices. And we know that because when we went from a 2D lattice with 256 vertices to one with 1024 vertices, it wasn't any better. And so my hypothesis, or say our hypothesis, mine and my students, our hypothesis is that the quantity is the degree of the graph. That the self-loops, the random self-loops, their weights must be small relative to the degree, not small relative to n. Our intuition for this, again, we don't have a proof, right? This is another installment of Tom Needs Help from the Mathematicians. Is for the complete graph, if you pick all the random self-loops to have values between 0 and 10, well, 10 is really small compared to the fact that each vertex has n minus 1 other edges. So for example, let's just look at vertex 3, right? If this self-loop has a weight of 10, like 10 might seem like a big number, but it's not big compared to the fact that there are all these other edges, and the number of these other edges is a huge amount because it's n minus 1. So for large n, if n's a million, then there's 999,999 of these other edges. So this one edge with a weight of 10 maybe isn't that significant. Again, this is just my intuition. It could be wrong. Versus if you have something like the 2D lattice, well, if one of these vertices has a self-loop with a weight 10, that seems very significant compared to just its 4 neighbors. And it doesn't matter how big this graph gets, each vertex still just has 4 neighbors. And so a self-loop of weight 10 is going to be more significant. So that's my intuition for why I think what matters here is that the weight of the self-loop be small compared to the degree of the graph. I want all the other vertices, all the, these normal edges here to overwhelm the self-loops. So that way the self-loops don't matter at the unmarked vertices. Okay, so let's try testing this hypothesis out numerically. So one way to do it is to, instead of doing the 2D lattice, let's try the 5D lattice, where each vertex now has 10 neighbors instead of 4 neighbors. So in this case, we're increasing the degree. And if my hypothesis is right, then we should get better agreement with the homogeneous case. So let's try that. So this is a 5D lattice with 1024 vertices. So we did 1024 vertices earlier for a 2D lattice. So if we compare those, we're not changing n, we're only changing the degree. We made it so that the weights at the unmarked vertices matter less. And for good measure, let's try making the unmarked weights between 0 and 1. It should be even better, and it is. So this is consistent so far with the hypothesis. Let's look at another example. Let's look at the hypercube. So this is a 10D hypercube, so it has 1024 vertices and degree 10. So here the degree is 10, so we suspect that if we have random weights between 0 and 10, it should make a difference, but maybe not as much as a 2D lattice where the degree is 4. So this should look more similar to this case, to this periodic square lattice where the degree is also 10. So let's see. Excuse me. So with no self-loops, we get this curve. With all the self-loops having the same weight of this value, 0.03, we get that curve. And making all the unmarked weights random between 0 and 10, we get this curve. And again, this is quite similar to the previous graph. So as we guessed it would be. And if we make the random self-loops have weights between 0 and 1, it should be much better, and it is. Okay, so that is consistent with our hypothesis. Another way to test our hypothesis is let's try upping the degree even more by looking at a 14-dimensional hypercube. So this does increase the number of vertices as well. So we now have over 16,000 vertices. But now with a degree of 14, we expect that having random weights between 0 and 10 should matter less. So it should be better. So with no self-loops, we get this. With all the self-loops taking the same value, we get that. With random self-loops between 0 and 10, we get this, which is actually a little bit better from the previous screen, or previous slide, as we guessed it would be. And then if we make the random weights between 0 and 1, it should be better still, and it is. So again, this is consistent with the hypothesis. All right, so before I conclude, I want to talk just really briefly about non-vertex transitive graphs, because you might wonder, everything I showed you was vertex transitive graphs. Does this observation hold with non-vertex transitive graphs? And the answer is actually no. Self-loops at unmarked vertices can make a difference with non-vertex transitive graphs. And we actually know this from prior research that I did with another one of my students, Mason Rhodes, who graduated a few years ago now. And he's now doing a PhD at the University of New Mexico, working on quantum computing. So we looked, so Mason and I looked at search on irregular complete bipartite graphs. So if it's irregular, then it's not vertex transitive. And what we found is that, if you make all the self-loops in one partite set weight L1 and all the self-loops in the other partite set weight L2, then basically the self-loops in the other set where there's no marked vertices, changing those self-loops do make a difference. So this observation that I showed you with all these plots, it seems like it only holds for vertex transitive graphs. So to conclude and summarize, so the hypothesis is that for vertex transitive graphs only, only the weight of the self-loop at the marked vertex matters, as long as the remaining self-loop weights can be, and the remaining self-loop weights can be chosen randomly, as long as they're small compared to the degree of the graph. And so that's our current guess. Some open questions. Well, there's the proof in general for the complete graph. Remember, we only proved the special case where there's two different weights. And then, of course, there's the proof or disproof of this hypothesis for vertex transitive graphs more broadly. And so if you want more information about this, again, Jacob and I published this in Physical Review A last year, and then it's also on the archive. And I'd be happy to take any questions.
Thanks, Tom. Any questions for Tom? So I do actually have a question.
Okay.
Will your observation work in the continuous time because of Anderson localization?
Well, I think it's because, so if you add self-loops that are all the same value to the continuous time quantum walk,
that's okay.
That's just adding,
right,
the same value to your diagonal, right?
Right, phase, just a global phase, yeah.
And so what you're basically asking is, what if you add different values along your diagonal?
Right.
And you can think of that as like, for example, having multiple marked vertices, right? So if you have self-loops of weight 1, and in other places self-loops of weight 0, you're basically marking the vertices that have a self-loop of weight 1. And we know that having multiple marked vertices can change the evolution.
But if they are all different.
Yeah, so for me, I'm giving an example of just having weight 0 or 1, right? That's already made.
Okay. Yeah.
And if you make it more extreme, right, besides the 0 and 1, you can have some that are marked more strongly than others. I would guess that would change your evolution. So I'm guessing that the continuous block might not have the same property that we observe.
Hi, Tom. Can I ask a simple question? So you have 9 types of arcs, right? And you're walking on arcs. So are you working on the quotient of the graph, really? Instead of the entire complete graph?
I think it depends on your interpretation of the math. I think as a physicist, I still think of it as I'm walking on the original graph. It just has an additional degree of freedom. But
I see.
But mathematically, it's probably equivalent to think of it as you're walking on the arcs. So it's up to you. It's up for interpretation, I guess.
Okay.
Yeah. Yeah, but I think of it as there's a particle at a vertex, and it has some additional degree of freedom that determines or that encodes what direction it's pointing. So that determines what direction it'll hop once you apply the shift operator. And we see this physically. There was a physical implementation of a 1D quantum walk where they use spin as a way to determine if the particle moved to the left or to the right, and it worked in a quantum superposition as well. So there was a spin dependent shift operator, which is what the shift operator should do. So I tend to think of it like that, but of course there's plenty of other physical implementations where they're not looking at even points in space as being your vertex, right? There's some that are based on time of flight or something like that for these optical based implementations of quantum walks. So in those cases, it's a very different way of thinking about it than having a particle at a vertex. So
did you choose the random weights uniformly from the interval?
Yeah, so in Python, I just used the random function to pick uniformly between 0 and 10, and it includes decimals, right? So any floating point number between 0 and 10.
Do you think it's gonna behave similarly if it's a Gaussian or something, a truncated Gaussian?
Yeah, so I think even if you didn't pick them randomly, if you just picked them all to have weight 10, and then the marked vertex has its whatever weight, 1 or something like that, it should still hold. So I think the random part,
okay.
I guess the random part is just to argue for the symmetry breaking and stuff like that, to show that. Because I guess the reason why I thought it was interesting is because I guess I imagine that part of the reason why these search algorithms work so nicely is because there's so much symmetry in these graphs. It feels very, very beautiful, and so the fact that you can get rid of all this symmetry but still have the success probability evolve in the same way, I thought was kind of interesting. Yeah, so even for search on the complete graph, right? You could have half of the self loops have one weight and the other half have the other weight, and it doesn't seem to matter except the weight at the marked vertex.
Hi, Tom. I was going to follow that up. So if you had very biased weights in one direction, that still wouldn't make a difference?
Yeah, I think in our simulations wouldn't make a difference, as long as the weights are small compared to the degree of the graph.
Right.
Yeah, it seems like that is the important fact.
It can still be very large compared to the weighting of the marked vertex, which is amazing.
Yeah, so that's part of the reason why we picked the value between 0 and 10. It's because 10 is big compared to if your self loop is supposed to have a weight of a half or 1 or
yeah.
So a lot of ones I showed you, it's 0.00 something, right? So
Exactly. So do you have any physical insight into why it's so robust? Because, it seems like it would get lost in the noise, right? I don't really understand it.
Yeah, so I gave a little bit of intuition for our hypothesis, and the idea is that this seems to hold for graphs where the degree also gets very big as your graph grows. For example, on the complete graph, right? If you have 1,000 vertices, well, that means that the degree is 999. So even though you have a self loop of weight, say 10, you have 999 other edges that have weight 1. So it seems like just having so many just unweighted edges kind of drowns out the fact that you have a self loop, even though the weight of that one self loop is like a decent size, right? If it's 10, but the idea is like 10 is small compared to 999 other edges, perhaps. That's my intuition for why we went with this hypothesis. Yeah, and then there's some examples I gave where instead of picking the weights between 0 and 10, like that was actually too big, and picking it between 0 and 1 was more appropriate for those graphs, because in those cases the degree was maybe just 4 or 10, versus 999 if you have 1,000 vertices. So
Thanks, Tom. That was neat. No questions. Let's thank Tom again.
thank you all for coming.